Hi, everybody, and welcome to Car Talk for March 10th, 2022. This is going to be a very special one because we're very excited to be welcoming Qichao Hu, who's the CEO of SES, to do this week's Car Talk and talk to us a little bit about the leading edge of battery technology, the advances that we can expect to see over the next few years. There's no question anymore that EVs have reached an inflection point, and if we're right about the advances in battery technology over the next few years, we're going to see EVs reach cost parity with internal combustion vehicles, and that's going to lead to an even greater disruption in the industry. The advanced battery technology companies that are pursuing these advances are the linchpin to all of this, and we at Wolfe believe that the fastest developing area within battery technology is actually within the anode of a battery. We'll talk a little bit about why and what that is. But that essentially is the component of the battery that stores lithium ions when a battery is charged. Over the next few years, we expect to see battery companies replace the graphite material that's typically used in anodes with silicon or lithium metal. And that's not going to be easy to do. But SES is regarded as one of the world leaders in the innovations that are needed to make that happen. They have a very innovative hybrid battery design that enables the use of lithium metal anodes. And we'll get into a little bit more about why this is a big deal in our Q&A. But as part of this introduction, I should mention that they have convinced several OEMs that are very sophisticated in this field that they have something special. They've gotten investments from General Motors, Honda, Hyundai, Geely, SAIC, and Foxconn. And we're looking forward to speaking about SES with Qichao. So Qichao, thanks for joining us. And I also want to introduce David Bell from the Wolfe research team. As many of you know, David was a battery chemist before joining our team. He's our resident expert in his field and has prepared a few questions for Qichao. But as always, we do want to get your questions as well. And you guys know the drill. It's the same as we always do at Car Talk. If you input questions, you just type those into the question box. We will ask them anonymously. We'll weave them into the discussion. But I know, Qichao, you have a few introductory thoughts that you wanted to convey. So before we kick things off, let me pass along to you.
Sure. Thank you, everyone. And it's definitely a really exciting time for the battery industry in general. And then just the past 1 to 2 years, every major car company, every major country has committed to transition to EVs in the next 10 to 15 years. And lithium metal is the next big thing. And there are different types of lithium metal, hybrid, solid state, anode-free, but the goal is the same. And then lithium metal not only offers higher energy density, longer range, but actually it allows OEMs to achieve lower cost. We can talk about that later, and also allow low cost materials like LFP to be more competitive with more expensive high nickel materials. And also, like you mentioned earlier, we are now working with several OEMs. Actually, we're the world's first company to sign an automotive A-sample joint development with OEMs in lithium metal. And then we are quite excited to make progress and then push this technology forward.
Thanks, Qichao. So I want to just dive right in here and really help set the stage. So investors have looked at a number of advanced battery technology companies. Some are looking to enable silicon, others like yourself, lithium metal, some are all solid state, some are hybrid. Why are all these new nanotechnologies important? You mentioned increased energy density. What value does that actually create for automakers?
Sure. So you can put all battery technologies in 2 buckets, lithium ion and lithium metal, right? And then lithium ion is basically graphite, silicon. Lithium metal is basically the anode is metallic lithium in the charged state. And there are different versions of lithium metal. There's solid state, there's hybrids, there's anode free, but the goal is the same. So what lithium metal offers is actually lower cost. So think of it this way. In lithium ion, you have two types of lithium ion. You have the value vehicles, which is typically uses LFP cathode, nickel-free LFP. It's low cost. And then you have the premium vehicles, which typically use high nickel cathode. So LFP in lithium ion gives you about 180 watt-hours per kg. High nickel in lithium ion gives you about 280 watts per kg. So LFP lithium ion is the current value vehicles, and high nickel lithium ion is the current premium vehicles. Now, once you go to lithium metal, you can take the same cathode. LFP in lithium metal gives you 300 watts per kg. And then high nickel lithium metal gives you 400 watts per kg. So now the new value vehicles can compete, can have the same range as the old premium vehicles. And then the new premium vehicles can give you range that's just not possible with current lithium ion. So this is hugely important to the OEMs. And this is why several OEMs, including GM, Hyundai, and Honda, have not only invested in us, but also invested in automotive A-sample joint development in lithium metal to achieve exactly that. Basically, to expand the envelope of vehicle designs so that the new value vehicles can have the same performance, same range as the old premium, and the new premium will basically enable new applications.
Thanks, Qichao. So we talked a lot how lithium metal could enable cost reduction, but let's dive into what's unique about SES's hybrid design, and how do automakers actually assess if it's more or less promising than some of your competitors, like a QuantumScape lithium metal battery, a solid power silicon anode battery, or even one of the liquid electrolyte batteries enabled by using an engineered silicon type material.
Yeah. So lithium metal. So first, lithium metal versus silicon, right? In silicon, you have different types of silicon. If you have low content silicon, say in the single digit or 10-20% silicon, then you can get to 300, 330 watts per kg. You really cannot compete with lithium metal. Silicon can only starts to compete with lithium metal once you get to 70% or more silicon. Then you can start to compete with lithium metal in terms of energy density. But then high content silicon, 70% or more, has a lot of expansion issues, swallowing issues, cycle life issues, performance issues, and then those materials need to be engineered, and the cost is not as scalable as just pure metallic lithium anode, either anode free or have a very thin C layer of lithium. So lithium has higher energy density and then is more scalable than a high content silicon. Now, within lithium metal, our hybrid approach versus other approaches in lithium metal is that our approach to lithium metal is, I would say, the most practical. So, for example, we have been working with GM since 2015, and then Hyundai since 2019, Honda also since 2020, and then we've done a lot of back and forth testing, and then we built small cells. We had actually back in 2019, we actually made these 4 amp-hour cells. These actually have 30 layer of cathode and 31 layers of anode. So that's totally 61 layers. And then last year, we expanded that to these larger cells. And this is actually 107 amp hour lithium metal cell. We unveiled this last year at the Battery World. So this actually has the same thickness as the smaller cells, both 30 layers of cathode and 31 layers of anode, so 61 layers. So our approach to lithium metal is the most practical because we've already demonstrated that we can actually build these large lithium metal cells using fairly mature manufacturing process. And then we actually built this using lithium-ion equipment. And then our team come from SK, LG, CATL. They have backgrounds in lithium-ion. So we've already shown that our version, our approach to lithium metal is more practical because we've built these large cells. This is a 107 amp hour lithium metal cell, and also we have we're the first to have automotive A-sample JDA with OEMs. We have one with GM, with Honda and Hyundai, and we expect to have maybe one more later this year. And then also now we are preparing to transition to B sample. And then the large 107 amp hour cells, we are making them in our Shanghai facility, in our Korea facility, and we started sharing data with our OEM partners. So just our approach is more practical than the other approaches.
So, Qichao, for those of the investors that are not as familiar with the company, could you give us the quick sentence on the design itself, why using a hybrid that includes a liquid actually could enable you to commercialize in a sooner time frame?
Sure. So the anode is metallic lithium, and the fundamental issue is that when you charge, you play lithium. You play these mossy lithium dendrites, and if you don't control it well, the dendrites could short the separator, and then you could have this cell explosion. So the way, and then when we started the company in 2012, we actually first used all solid state approach. And then we actually abandoned that approach in 2015 because we realized, yes, all solid state can help suppress dendrites, but then you have all these other issues. The performance is poor at room temperature, and it was just really difficult to make a cell. So we switched to this hybrid. So the way we address the mossy lithium formation is step one. We have a liquid electrolyte, but it's a new type of liquid. It's a high concentration solvent and salt liquid. And the salt is totally different. The solvent is totally different. We actually design the solvent in-house, and then we actually make the solvent in-house because we just cannot buy it. And then in the past 8 to 9 years, we've gone from generation 1 to now we're on generation 12 electrolyte. So this high concentration solvent and salt, we make that in-house. It's very stable on lithium metal. And then when you charge, you still play lithium, but under the microscope, you can see the morphology, the structure of the plate lithium is very different. It's much denser than conventional plate lithium. It's denser, it's smoother. You don't have these needle-like structures. So step one, we use a high concentration solvent and salt liquid electrolyte. That's non-flammable, non-volatile, and then it's very stable on lithium metal to basically change the way plated lithium looks like, change the morphology of the plated lithium. So it's very dense. Step one. Step two, we have another protective coating between the separator and the anode that further suppresses this plated lithium, and then makes this plated lithium even denser. And then step three, outside of the cell, we use software to optimize the environment, the pressure, the temperature, the charge current density, discharge current density, to also get the most optimal play lithium. Like everything we do, the high concentration solvent and salt liquid electrolyte, this protective coating between separator and anode, and the software is to do one thing, to densify this plated lithium. If you can play 100% purely dense lithium, then you will have very good cycle life and very good safety. But in reality, you will never get to 100%. You'll get to, when you started, 80%, 92%, 97, 99, 99.2, 0.5, 0.6, 0.7. Now we're close to 99.8%. We'll get closer and closer to 100% dense lithium when you play it. If you can play as close to 100% dense lithium, then you improve the cycle life and the safety. It's all
Thanks,
about
Kichao.
justifying the play lithium.
Yeah, and I would add, I think the most critical part of what Kichao is mentioning with plated lithium is to prevent dendrites, which we've written about a number of times, which are the stalagmite type structures that could short the battery. So this is how they're preventing them. So let's quickly transition to the technical hurdle. So you just showed us that really amazing 100 amp hour cell, which is cool to see. It's quite large.
It's a real cell.
Could you walk us through what challenges you're now facing as you start to manufacture more of these cells? What should investors be looking for in terms of performance metrics for these large 100 amp hour cells?
Yeah, so one example, for example, the smaller cell, 4 amp hour, 107, same thickness, but right now we actually published the third-party tested data on the smaller cells, and the performance of the bigger cell is much worse than the smaller cells as of now. And we're trying to optimize that. For example, when you go from the smaller cell to the larger cell, even though it's the same number of layers, 61 layers, for example, the amount of electrolyte you can put in is different. And also the pressure distribution, current distribution, uniformity, all those are different. And then the smaller cell, we've been making this since 2018, 2019, and we've spent a lot of years optimizing that. And then now we really have to optimize the cell design of the larger cell to get to the same performance as the smaller cell. That's possible. It's just we need to put in the work to really optimize the cell design, because now it's a larger cell. It's like in Tesla, you go from 1865 to 2170 to 4680. When the cell gets bigger, taller, and fatter, you have to change the cell design. For example, the bigger cells, you have to add more taps to ensure the current distribution is more uniform. Same thing, when you go from the smaller 4 amp hour to the 107 amp hour, we really have to take the time to optimize the cell design. So that's one thing that we are doing. And then also at the material level, anode, this thin lithium on copper, for example, no one in the world today can make anode this wide. No one makes that today. And then that is one supply chain issue that we are trying to resolve with our partners. And then we'll probably make some announcements later, making this thin, wide format lithium anode, and then also electrolyte. Our high concentration solvent in salt is quite unique, the solvent, and how to synthesize that at larger scale, but also ensure the same purity. So I would say it's a combination of optimizing the cell design, and then also developing and securing the key materials for these larger cells. And then the plan is we actually started working on A samples last year. We're going to complete A sample by end of this year, and then second half of this year we're going to transition and start preparing for B sample next year, and then second half of next year we're going to start preparing for C sample in 24, and then eventually get to start of production 25.
Can I just ask, how does when you say that the performance is not as good yet with the 107 amp hour cell, like what is the metric that is the most important for us to ask you about? Is it cycle life, or is it what can maybe just give us a few landmarks of what we should be?
Right. So this cell and this cell, same material, exactly same cathode, same electrolyte, same loading, same everything, same number of layers. This one we can get to 300 cycles to 500 cycles, depending on the charge and discharge rate. But this one, initially, the first batch we built it was about 10 cycles, then we improved it to 50. Now we're about 150, and we continue to improve this to the same performance as the smaller cells.
And what is your objective? What would be an automotive grade cell in terms of cycle life?
Yeah, so this year our target is 300 cycles, silver 3 hours charge and discharge, and then 500 cycles slower charge and 3-hour discharge. That'll be the cycle life target for automotive A samples.
Okay.
For the large 107 amp hour cells.
So that would mean, so if we this goes into the vehicles that say have 300 miles of range, you would have something like 150,000 miles in theory, at 500 cycles, something along those lines, 150,000 miles of sort of durability
So,
battery.
right. So, not quite. So, the current lithium-ion EV can go about 300 miles, right? Once you switch to lithium metal using the same cathode, you can go about 500 miles. So
Okay.
500 miles, then 500, yeah, then it's about 250,000 miles.
Gotcha. Okay. Thank you.
Okay. Thanks, guys, for that question. So I want to dive in a little bit deeper into what you were mentioning on the supply chain. So we know today the supply chain for lithium metal anodes does not really exist. One, how are you working to help build this out? You know, what sort of scale do your suppliers need to achieve in order to actually enable a reasonable cost for your bill of materials?
Yeah, yeah. So if you look at our shareholders, TNT Lithium, one of the largest lithium mine in the world, is our shareholder. And then we're also working with another company. They're actually the largest producer of lithium metal to basically expand this production capacity of thin wide format lithium foil. And then we expect second half of this year we can actually get the line to a point where we have enough lithium foil to produce several thousands of cells, large 100 amp hour cells per month. So enough for about 0.2 gigawatt hours. So we're building Shanghai Giga phase one, and then that is about 0.2 gigawatt hours. Shanghai 2 Giga phase two next year will be about 1 gigawatt hour. So this year we're going to get the line set up to produce enough anode for 0.2 gigawatt hour this year, and then multiply that, also improve the line efficiency towards end of this year, so that next year we can have 1 gigawatt hour capability.
Okay, thanks, Qichao. So one question which I think is from the audience, and we've all seen what's happened over the last couple of days with nickel. So we're all watching these rising battery metal commodity costs increase. Could that
Yes.
actually derail your plans? And do you have any views on the wider BEV market? Could this derail the achievement of cost parity for BEVs across the board?
Yes, I think for nickel, definitely the price really spiked. So two options. One is, so nickel is used for the premium vehicles, right? Either nickel, high nickel lithium ion premium or high nickel lithium metal premium. So one way is basically pass the cost down to end users. That's one way. Another option is basically, instead of using high nickel cathode, we can use nickel-free LFP cathode. And that's actually what, so in all the JDAs that we have with OEMs, we have two parallel tracks. LFP for their value brands like the Chevy, the Hyundai, and then high nickel for their premium brands, the Cadillacs, the Ioniq, the more expensive brands. So as I mentioned earlier, LFP paired with lithium metal can give you same or even higher range as high nickel in lithium ion. So again, LFP paired with lithium metal, the new value vehicle can get you the same range and performance as high nickel lithium ion, the old premium. So lithium metal, I mean, people like LFP because it's low cost, but they don't like it because it's got limited range. So lithium metal actually allows LFP to be competitive with high nickel in lithium ion. So we can actually move away from nickel and then use more LFP in lithium metal and then still get the same range as high nickel in lithium ion.
So Qichao, I'm sure you're getting a lot more and more interest in LFP. We hear you're developing it in parallel with high
Yes.
nickel. You know, in the past, LFP was highly concentrated in China. and now we're seeing more interest for the Western OEMs in incorporating it.
Yeah.
You have relationships with both the Western OEMs and Chinese OEMs. Could you walk us through the exposure you could see with LFP increasing its usage with the likes of companies like GM, Honda, and Honda?
Yeah, yeah. Even Tesla a few months ago announced just all their standard Model 3 will have LFP, right? Not just in China, but also outside of China. And I think to the OEMs, at the end of the day, the end users don't really care if it's LFP or NCM in the cathode of their battery. What they care about is this envelope, cost range, and this overall envelope of capabilities. So as the price of nickel goes up, then LFP becomes more attractive from a cost perspective. LFP is already attractive from a cost perspective, and then as this delta gets even bigger, LFP becomes even more attractive from a cost perspective. And then the question is, on the anode side, can you use a material, a design to increase the energy density of LFP? So if lithium metal can allow LFP, so LFP could never compete with high nickel from energy density perspective. But if you pair LFP with lithium metal, then you get 300 watts per kg, whereas high nickel in lithium ion, you get 280. So lithium metal actually helps LFP become more competitive with high nickel, and all the OEMs that we are working with, they sell, of course, a lot to the U.S. market, to China market, to Europe market, and definitely we're seeing a renewed excitement to LFP.
Okay. So I want to continue on this materials topic and touch on sourcing. So your plan is to be a complete battery manufacturer. You're going to compete with the likes of LG, SK. Could you walk us through your strategy for securing these materials upstream? And we're specifically wondering, have you already secured long-term contracts based on your current manufacturing plan?
Yeah. So on the cathode, we are working with a few mine producers. Actually, our spec partner is Ivanhoe. They produce nickel and copper. That's actually one of the key reasons why we really like Ivanhoe. So on the raw material side, we are working with a few partners to secure long-term supply. And also in the OEM JDAs, typically the OEMs will help you source the cathode. Actually, in some cases, they will source the cathode for you. For example, they will say, okay, they'll actually buy LFP for you and then say, you use these LFP for the Chevy and the Hyundais, and then you use this high nickel 90%, 88% high nickel NCM from these guys for the Cadillacs and the Ioniq. Typically, the OEMs will source the cathode for you, and then we need to secure anode and the electrolyte, because anode and electrolyte are the two materials that are quite unique to us. So on the anode, we expect to make some announcements later this year, basically to secure this wide format thin lithium anode. It's absolutely crucial for us. Same thing on the solvent, and also the separator. Last December, we announced exclusive supply with Entech. And then going forward, we will definitely work on securing these materials, especially anode and electrolyte, because those are unique to us, whereas cathode is basically commercial off the shelf, and then will likely be sourced for us by the OEMs.
Thanks, Qichao. So transitioning a bit into the commercial agreement. So we talked about the 6 OEMs that you're working with. 3 of them you mentioned have now signed A-sample joint development agreements, GM, Hyundai, and Honda. What needs to happen along the development to turn these into supply agreements? And furthermore, you've also received investment from a couple of cell manufacturers. What role, if any, are they playing in the development of your technology?
Yeah. So the first one, right now we're in A sample. A sample is basically solve all the technical challenges. So this cell actually is very close to meeting all the specs, cycle life, everything. So basically A sample, the big cell has to have the same performance as the smaller cell. So that's A sample. We're quite confident that we can improve the performance of the large cell and then to meet the specs. And then next, we need to get a B sample. B sample, then we have to convince the OEMs that we have a supply chain strategy, that all the key materials we have not only secure the supplies and the supply is sufficient for the future volume, also cost. So B sample is really A sample, but then you make it a few times, typically 3 to 5x more, and then you have to demonstrate that you have secured the supply chain. And then after that, C sample, then we typically would put these batteries in several hundred demo cars, and then just drive those cars for 9 months to a year, and then just test everything. And then once that's done, then we can move on to commercial contracts. And in terms of the cell manufacturers, currently we work directly with the OEMs, it's just SES and the car companies. The thinking is once we get to C sample and also have commercial contracts, we could form joint ventures with the OEMs, the car makers, and potentially their large scale cell manufacturers to share the risk, to learn large scale manufacturing from them in a joint venture.
Thanks, Qichao. And on that note, there's a quick question from the audience here. So you mentioned in C samples that you could do a few prototype vehicles. Would you ever actually commercialize a limited run of high performance batteries that use their technology, or are you focused on the more mass production type vehicles?
Absolutely, we would. So the general passenger vehicles like the GM, Hyundai, and Honda, because it's to the mass market, the driver could go from grandmothers to 18-year-old. So the process is pre-A, A, B, C, very, very rigorous, no shortcut. But these cells, actually, even the current cells, we can actually build them into modules and then packs, and then we actually have these modules and packs, and then we could use them in commercial vehicles, fleet vehicles, delivery vans, autonomous vehicles, drones, and near-term commercial applications that don't have that long process, so that we could potentially achieve revenue much sooner. But yes, absolutely, we plan to do that.
Okay, so let's circle back to one of the key points I think that you brought up when we started the conversation. So one of the great advantages of SES's technology is it could be compatible with existing manufacturing equipment. And on paper, it seems like you do have the easiest transition to manufacture batteries at scale out of the lithium metal companies that we speak to. Could you update us on what scale you've achieved today, and how are you proving out that you can take advantage of the same equipment that legacy cell manufacturers are using?
Yeah, so ever since 2016, even when we were developing the smaller cells, all the cell engineers and manufacturing workers that we've hired in Boston, in Shanghai, in Korea, they're all people from SK, LG, CATL, lithium-ion companies. And they join, and typically within 1 or 2 months, they become really good. And then all the equipment that we have purchased, we actually purchased these from equipment manufacturers that manufacture lithium-ion equipment. So the cell process, basically, cathode is the same, electrolyte material is different, but it's high concentration liquid, and then stacked pouch cells. The entire cell assembly process is the same. The only difference is the anode, but other than the anode, the entire cell manufacturing process is the same. So we have And currently in Shanghai Giga phase 1, we are at about 0.2 gigawatt hours capacity. So we can actually make these large 107 amp hour cells. We can make close to a few hundred to 1,000 per month now. And then as we continue to solve the anode shortage, the anode limitation, we could get to several thousand of these large 100 amp hour cells per month. So now we are at 0.2 gigawatt hours, and all the engineers are from the large lithium-ion companies, and the equipments are made by companies that make lithium-ion equipment. So really the manufacturing process, I think we have demonstrated that it's very similar, except the anode, which is totally different, but everything else is very similar to lithium-ion.
Can I maybe just chime in to clarify one thing? We were talking about, I just wanted to maybe get a little bit more clarification on the costs. So you talked about the LFP being value and nickel being more premium. So what we know today in the world, maybe it's not the case today given what commodities have done, but maybe a year ago we were talking about these cells, the nickel cells being close to $100 a kilowatt hour, and these iron phosphate cells maybe being closer to 80, something along those lines. So if we think about that as a benchmark, what could you guys achieve as a result of the increasing energy density? Is there a way for us to maybe frame that?
Right. So there are two ways of looking at it. The easy way will be that $100 per kilowatt hour and 80. Now that $100 obviously gets you longer range, and that 80 gives you shorter range. When you go to lithium metal, that $80 LFP lithium metal will give the same range as that $100 high nickel lithium ion.
Mm-hmm.
So that's the cost saving, but you still have the same range at the vehicle level.
Okay, so effectively, am I correct in thinking that this is initially a 20% cost reduction effectively? Because, you know, you'll get the same amount of kilowatt hours.
Yeah.
Basically a 20% lower cost per kilowatt hour.
Yes, by switching to a nickel-free cathode.
Right.
And the cathode accounts for about half of the BOM. So if the cathode is cheaper, your whole cell is cheaper.
Okay. And you also talked about the path from A sample to B sample and how that's going to proceed. Maybe just to frame when do you actually enter a commercial production that would wind up in a vehicle? What are the things that we should be looking for? What's the timeline for ramping that up?
Yeah. So the typical process is pre-A sample, A sample, B sample, C sample, and then SOP, start of production. Typically, when you're in C sample, it's already similar to commercial production. So we started A sample last year. We expect to complete A sample end of this year. And then second half of this year, we expect to start preparing transition to B sample. And then next year, 23, end of next year, we're going to complete B sample and then transition to C sample. So end of 24, we complete a C sample, and then 25 SOP. So C sample and SOP around 25, we expect to start commercial production.
Okay, thank you. David?
Thanks, Qichao. So I think what would be great, since we're coming up close to the 45 minutes, could you walk us through your business plan longer term? What sort of total addressable market are you thinking about mid-decade and end of decade? If SES is successful, what kind of market share could you hope to achieve? Are you looking to capture the entire BEV market share for your respective OEM partners or a percentage of it? And lastly, if we could just touch on a bit the economics of the business. So we briefly just touched on the value you could enable, but maybe if you touch on pricing and margin a little bit.
Yeah, so actually, in the near term, from now to 25, we plan to focus on A sample, B sample, C sample. And then in the initial production, 25 to 27, we're going to focus on producing the cells and the modules in a type of joint venture with the OEMs. So I think in the near to midterm, the focus is on supplying the cells. But in the long term, there is another opportunity that I think is very exciting, not only to us, but also to any innovative battery companies that are thinking about this, and that is data. So one thing that we have found is extremely important to this industry is data and safety, because batteries just, it's impossible to be 100% safe. One thing that we start working on and the industry started working on is collecting data, massive amount of data from raw materials, the purity, the concentration, the battery materials, to the manufacturing process, the hundreds of steps, every step, every component of the entire process, you really try to track all the data. And then once you have the batteries, formation process, and then the cells are integrated into modules, packs, and then the packs, you can supply the packs to vehicles, you can lease the packs to end users, and then once the packs are incorporated in the vehicle, we also continue to monitor the battery health, how the user is driving the car, is charging the car, is the car parked in the garage, is the car parked outside, and basically monitor battery health 24/7. So you build this digital twin of the battery, and then in this process, you can also track the CO2 footprint. Lots of OEMs actually, when they buy batteries, they ask for the CO2 footprint, because then you have to offset it by through some type of carbon trading. That actually now is actually quite prevalent in China and also Europe. Several OEMs have that. And then at the end of life, you can also use this data to do recycling. So we talk about the rising cost of nickel and these raw materials. If we can have these recycling technologies, then you can think of okay, the first battery, you use materials from a mine, but in later lives, the car becomes the mine, right? You can use the lithium, the nickel that's already in, you can recycle the material that's already in this car. So I think in the long term, in addition to just supplying the battery, there's opportunity to provide data and safety prediction to either the OEMs or to the end user, or to our cell manufacturing partner, to improve safety and also to lower the risk. For example, if you have 10,000 vehicles in the field and the 5 have issues, instead of recalling all 10,000, you know exactly which 5 have issues. You just recall those 5. So I think there is a lot of opportunity to capture additional value beyond just supplying batteries, potentially battery as a service to the end users. In China, CATL started using introduce this battery swapping solution to some OEMs, so the battery company could actually lease the battery to the end user and then capture additional value that way. So I think especially the long-term business model is actually quite open, not just to us, but also to the entire industry. Of course, now we are an integrated, full-blown cell supplier, but the industry, where the EV battery industry is heading, I think that's quite open. Even the larger players are already starting to look into how to capture additional value beyond just supplying the hardware.
Qichao, I just wanted to chime in with one additional question, if we can. Is there anything you're willing to say on what the total addressable, what sort of market share you guys could hope to achieve by the end of the decade, and what sort of gross margin you could target with those batteries?
Yeah, I mean, we have the numbers in the financials. I think we expect 30%, and then roughly in that range. But I think so. Those are the numbers that we talk about. But I don't want to say, not just by end of this decade, even the next 5 years, the battery industry is going to change dramatically, and we will see new business models, entirely new business models, and these business models, especially for battery companies that are thinking about not just the battery itself, of course that is a core, but data and how to track data and safety throughout this supply chain. These battery companies are at a very good position to potentially capture far greater value than the current business model.
Okay. So I think that's it for today for questions, unless Rod, you want to chime in with anything. But I want to thank you again, Qichao, for your time today. I hope the investors learned a little bit more about the company. And as always, I think Rod and I are both available, and the team is available to field any more questions.
Thank you very much, Qichao. It's good seeing you again.
Thank you, guys. Thank you, everyone. Thank you.